last time we had an Australian exoplanet workshop. I talked about planet formation imager. I'll just put up the website for this. I'm not going to talk about it this time. This is a post-ELT instrument. So what about before the ELT? Can we do some very interesting things, especially now that Australia is part of ESO? Terrestrial planets and also young planets. So firstly, I'll summarize in 3 slides what Frank just said. So some people thought that this telescope called Spitzer, which cost $1 billion, was very interesting for studying exoplanets. That's because you could burn these little black dots, which is the flux of a hot planet when it goes behind the star. You see a very, very small deficit in flux, and there's many, many papers on this. So this is 2 × 10⁻⁴ at 1 sigma. That's the contrast ratio you can get with lots many hours. That's for $1 billion. So if you go to JWST, you go 2 × 10⁻⁵, 10 times better, with 100 times as much light as you collect. You also have 10 times as much photon. So if you're doing the same thing, you might be able to maybe get down to getting reasonable errors on a 700 Kelvin planet. You might get some sort of a spectrum, but it won't be very high to noise. This is going from 2 × 10⁻⁴ to 2 × 10⁻⁵ for $10 billion. And so what Francis talk was going to 2 × 10⁻⁶, not for $100 billion. That's with what the scaling relationship that I showed you on 2 slides that I've given you. But for $10 million, including most of that is the cost of the telescope time, which Australia's already paid for, and France has already paid for. So this is not, of course, a secondary eclipse. This is kind of like imaging, but with an interferometer, kind of like the way 51A was discovered. And so there's a collaboration of people that include several people in this room, Barnaby, Peter, and led at the moment out of Liège, high contrast interferometry for 5 microns. We're looking at a way as a visitor instrument to get this thing on the VLTI. It does include people at Observatory de Paris Meudon as well. Okay, so just a quick slide on the phase errors. So what limits this nulling kernel intensity that Francis talked about? So there's thermal background noise. There's, as I published in 2013, for these sort of quantities, you have to, if you have phase errors in the system, then the noise you get at the end is proportional to the cube of these phase errors. So if you have 50 nanometers phase RMS, which was achieved as sort of in post-processing with a SUSY interferometer in Narrabri, was achieved by Panama test bed interferometer in the US, then you know this noise source only means you have to negate for 1 hour to detect things at this level. Of course, with the existing 4 times worse phase RMS as the VLTI gets, it's more like 10,000 hours. So this is a solvable problem. It's been demonstrated that it's been solved, but the existing infrastructure doesn't do it. So one has to be able to track the phase of the fringes somehow, basically take VLTI and put it in space with what's called a fringe tracker at shorter wavelengths. And that has to be done, I would argue, first before we build this node. And you can also say, how about the residual shot noise of the target? Turns out that's not important compared to the thermal background noise. Once you get to a null of 100 to 1, so you block out 99% of the starlight, and that's already been achieved. And one thing I'm certainly not going to talk about, but I have to talk about in the coffee break, is how you calibrate this and deal with instrumental slow drifts. I don't think this is a difficult problem. Okay, so the issue, as I was sort of saying, is that VLTI only have 1 fringe track, only 1 way to basically take into account the effect of the atmosphere between the telescopes and act like the interferometers in space. So it's kind of like the terrestrial planet finder interferometer and Darwin concepts before. It's quite complicated, very, very complicated. Elodie Choquette, I can't remember how you pronounce her last name. Anyway, she has done a very detailed study on what you could do with quite conservative assumptions, but in an ideal situation with the gravity system, and you're not going to get down to this 50 nanometer RMS. So you need something that's a little bit better. A little bit better would mean you run the camera at 2 kilohertz instead of 1 kilohertz. The camera you use can run at 4 kilohertz, so that's fine. You increase the wavelength range to have the shorter wavelengths, ones that are like bright, typical planet hosts, but you can't see the galactic center, which is what this was about. Throughput it has to have higher throughput, which is also quite easy to do. So this is an Australian-French opportunity. So Australia's now part of ESO. There's the handshake that happened 6 months ago. sort of think about the technology we're talking about here, so certainly nulling has been a French thing. When I talk about the best way to build a fringe tracker that's simple and efficient, you'd use something that would either be called redundant pupils, like Maximas, or a partly densified pupil, which is what France's PhD supervisor talked about a long time ago. A very simple thing where you just take the 4 telescopes, put them next to each other, you make fringes, kind of like a double slit experiment, but with 4 slits, and then you can track these fringes. And it turns out that's about a factor of 3 to 5 more efficient, even in a single wavelength channel, than the gravity beam combined. How am I going to try and sell this to the Australian community in a bigger way? Well, not just fringe tracking, this can measure the separations and contrast ratios of thousands of nearby metal core binaries, which are essential for galactic archaeology. And these are things that will be detected with the Gaia spacecraft, which is going to, of course, have its new data release later this year, and I'll have binaries in a couple of years' time. So that's topic 1. How many minutes do I have? I've got plenty of minutes. I'm going very fast, which is good. But anyways, that's finishing up on what France was saying. That I think there's a way that we can do 10 times better than DWST for 1,000 times smaller price for self-luminous or irradiated giant planets. So how about habitable planets, part 2. Again, this is before ELT. So Kepler, amazing detections, many habitable planets. Most stars have planets, all these wonderful results, of course. Kepler's relatively narrow cone mostly detects planets around stars that are sort of 200, 300 parsecs away, and they're very hard to study up, to study in finer detail. Mostly led by JPL, I would say. There's had been many studies on how to directly detect light from Earth-like planets, and there's TPFC, TPFI, showed it's very definitely possible. No technological problems at all. We can do this, but the price tag is a little bit above JWST. How else could we do it? So this is directly not from me. This is from Olivier Guillon, the Subaru telescope. You're going to sort of plot all the nearby stars, and you plot a sort of a yellowy-green circle for a G-type star, and a red circle for an M-type star. Most of the nearby stars are M-type stars, not M5 stars, not ones like Proxima Centauri, where any habitable planets or habitable zone planets would be tightly locked, but slightly more massive M stars. If you say for a 30-meter telescope, how many of these are accessible to an in principle perfect AO system and chronograph for detecting planets in the habitable zone, you actually have quite a lot of them. They're all red circles, they're not yellow circles. So you need to have $10 billion in space to get to the green or the yellow circles. For the red circles, a very good adaptive optic system from the ground pretty much gets you to detections of planets in the habitable zone down to Earth radius. So the one we know, of course, is Proxima Centauri b. I don't think it's all that controversial. If Duncan runs here, he might have some points to make, but the point is there are 3 telescopes that all measure a very small signal. And this is just the tip of the iceberg. This is a super Earth. If it was 1 Earth radius instead of 1.1 Earth radius, I don't know if it's detected. Angular separation is 30 milliarc seconds. So it's definitely not something that you can do with the infrared with a single telescope. And from the results from Kepler, we expect most M3 dwarfs nearby the Sun to have terrestrial planets. Many of them will be cloudy and reflect a lot of light. So how about the technology? So 10, 15 years ago, the idea of a chronograph that could get you to contrast above 1,000,000 to 1 were silly. As Franz showed, we show part of this as a stuff called PIAA. Chronography is now, I would say, a solved problem, other than which company used to manufacture the bits. And there's some fancy things you can do there. Wavefront control. Wavefront control is, in principle, a solved problem. There are no working adaptive optic systems in the world there. By working adaptive optic system, I mean something that, this is Guillon 2006 paper here. Working adaptive optic system is something that's within a factor of 2 of having optical sensitivity. And all wavefront sensors, this is a noise parameter. 1 is perfect, 10 is bad. All existing extreme area systems are a Shack-Hartman wavefront sensor, with the exception of modulated pyramid, which modulate too much and are almost the same as a Shack-Hartman wavefront sensor. They're about a factor of 10 worse than they should be. But that technology is solved, and it's just a matter of having a Woolford tweeter AO system. AO system that can sort of get you close, and then use an optimal wavefront sensor to get you all the way there. I'll skip this slide. So if you stick one of these good AO systems on a chronograph, and behind that you put something like wax, the ANU 2.3-meter telescope, you have something that I've called Siren. Ignis Snellen group has put some papers out on this as well. You basically have some reflected light from a planet orbiting a star. And so this is, I put this out actually just before the Proximus NB was discovered. And you can see that the reflected light is redshifted and blue shifted. And so you can get this extra level of self-calibration by subtracting out the starlight, and what you're left with the redshifted or blue shifted light. And there's a few things you could detect for an 10-meter class telescope, many at 20 meters. And of course, if you have reflected light, you're going to see the spectrum of the star redshifted or blue shifted. You see on top of this imprint that a signature of oxygen. And if you do this in polarization, you see the electron reaction. So these are difficult things to do on 8-meter telescopes, but they're certainly not impossible. And you'd get very close for an Earth radius planet on an 8-meter telescope with an ideal system, and it would be not too difficult with a 30-meter telescope at all. This is what we hear. It's oxygen may or may not be a sign of life, but with the right initial conditions, so with the right planetary conditions, we can eliminate the other causes of oxygen. It's sort of the big signature. So I have no minutes, so I won't talk to you about the details of signal to noise, but I will point out that there's a thing called the Viz-Macau system, which includes a bunch of people. It doesn't formally exist yet, there's no formally so called, but it will exist. And it has people from France, Australia, maybe Observatory as well, but basically it's a laser guide AO system with a woofer and a tweeter AO system, so a coarse and a fine AO system, a Shack-Hartmann, and some sort of focal plane wavefront sensor. And there's a design study that doesn't call this an AO system, an extreme AO system, it calls it a wide field AO system for fuzzy galaxies. There's actually only a couple of tiny changes you'd actually make to make this extreme AO system that is reflected light exoplanets. I'm happy to take questions, but I'm out of time.